Welcome to today's paper reading. Today's paper is titled, LEGO, Learning Egocentric Action Frame Generation via Visual Instruction Tuning. This paper was published on AR14 by Bolin and colleagues from Gen AI, Meta. The core problem addressed in this paper is the generation of instructional images depicting human daily actions from an egocentric viewpoint. This is crucial for efficient skill transfer. The goal is to synthesize an image, known as an action frame, which is contextually relevant to the user's situation. However, existing egocentric action datasets are limited by the lack of detailed annotations that describe the execution of actions. Additionally, current diffusion-based image manipulation models struggle with controlling the state transition of an action in egocentric image pixel space due to domain gaps. To overcome these challenges, the authors proposed the LEGO model, which involves visual instruction tuning to generate enriched action descriptions. This approach enhances the performance of diffusion models by leveraging image and text embeddings from a visual large language model, VLM. Figure 1 illustrates the process of obtaining task-specific instructions using different models. Initially, a user queries a large language model, LLM, for guidance on a complex task, receiving a generic response that requires translation to fit her specific situation. When the user's prompt is augmented with an egocentric view of the scene and passed to a visual LLM, the instructions become more contextualized to her current environment. However, the user still faces the challenge of interpreting written descriptions. The novel LEGO model addresses this by using the combined image and prompt to automatically generate visual guidance from the egocentric viewpoint, allowing the user to complete her task seamlessly. The novel problem introduced in this paper is the generation of egocentric action frames. Given a user's query on how to perform a specific action and an egocentric image capturing the moment before the action begins, the goal is to synthesize an image illustrating the action's execution from the same perspective. Two major challenges are identified: the lack of detailed action annotations in existing datasets, and the domain gap between egocentric and exocentric views in diffusion models. To address these challenges, the authors proposed the LEGO model, which includes a prompt enhancement scheme and the incorporation of visual and text embeddings from a fine-tuned VLLM to improve image generation performance. The recent advancements in diffusion models have significantly enhanced text-guided image manipulation capabilities. These models are applied in various tasks such as image restoration, style transfer, and personalized image synthesis. Techniques like SDEdit and null text inversion are used to manipulate images in the latent space. However, a major challenge is the requirement for accurate image captions, which are often unavailable in egocentric datasets. Additionally, the control of action state transitions within egocentric image planes using diffusion models remains an unexplored area. In the field of egocentric vision, significant progress has been made in understanding human actions and interactions from an egocentric perspective. Models like EGOVLP and its enhancements through multimodal fusion have been pivotal. Additionally, generative adversarial networks, GNs, have been used for tasks such as future head motion and gaze anticipation. This paper introduces a novel approach by leveraging very large language models, VLLMs, and diffusion models to generate action state transitions specifically on the egocentric image plane, marking a new frontier in this domain. Figure 2 illustrates the process of data curation using GPT 3.5 for generating detailed action descriptions in egocentric vision tasks. The figure shows how detailed action descriptions are provided for several example images, along with their action labels and bounding boxes, to facilitate in-context learning. Additionally, a new action label and bounding boxes are input as a query, and GPT 3.5 generates descriptions with enriched information highlighted in the response. This process aids in creating a dataset with comprehensive action descriptions, crucial for training models to understand and generate egocentric action frames. The LEGO model involves fine-tuning a visual large language model, VLLM, using visual instruction tuning to generate enriched action descriptions. These descriptions are then projected into the feature space of a latent diffusion model, LDM. The LDM is trained to synthesize egocentric action frames based on the input frame and the enriched action description. For visual instruction tuning, GPT 3.5 is used to generate detailed action descriptions from input queries composed of action labels and object bounding boxes. These descriptions are used to fine-tune the clip visual encoder and the LLM. In the action frame generation phase, a latent diffusion model is employed to synthesize the action frame. The UNet conditioning component is designed to interpret egocentric actions correctly, using VLLM embeddings to bridge the domain gap. Figure 3 provides an overview of our proposed LEGO model, which is designed to generate egocentric action frames. The process begins with fine-tuning a visual large language model, VLLM, to produce enriched action descriptions through visual instruction tuning. These enriched descriptions are then projected into the feature space of a latent diffusion model, LDM. The LDM is trained to synthesize the egocentric action frame, taking into account the input frame, the enriched action description, and the VLLM's image and text embeddings. This approach leverages the strengths of both the VLLM and the LDM to bridge the gap between visual and textual understanding, resulting in more accurate and contextually relevant action frame generation. In our experiments, we utilized two well-established egocentric action datasets, Ego4D and Epic Kitchens, and employed a variety of metrics including image-to-image and image-to-text similarity measures, as well as a user study for human validation. We compared our proposed LEGO model against previous state-of-the-art methods such as ProxEdit, SDEdit, and InstructPix2Pix. Our model demonstrated significant improvements in both quantitative metrics and qualitative visualizations, as well as higher win rates in user studies. Additionally, we conducted ablation studies to understand the contribution of enriched action descriptions and the role of VLLM embeddings, highlighting the importance of visual instruction tuning in enhancing model performance. Figure 4 presents the results of a user study conducted to evaluate our model and baseline models. The win rate, which is the percentage of times each model was selected as the best, is used as the primary metric. The study involved 60 examples from each dataset, with generated frames from our model and baseline models presented to raters on Amazon Mechanical Turk, AMT. The raters were asked to select the image that best aligned with the provided action label, while preserving the most contextual information from the input frame. To minimize bias, 5 AMT raters annotated each example, resulting in 300 samples for each dataset. The user study interface is detailed in the supplementary material. The results show that our model surpasses the best baseline by 44% and 38.34% respectively on Ego4D and Epic Kitchens, validating the superiority of our model. Figure 5 presents a visualization comparison between the proposed LEGO model and several baseline models on two datasets, Ego4D and Epic Kitchens. The first 3 rows display results from Ego4D, while the last 3 rows show results from Epic Kitchens. The LEGO model demonstrates superior performance by generating action frames that more accurately align with user prompts and retain a greater amount of contextual information from the input frames. This is in contrast to the baseline models, which either fail to understand the user prompt or generate frames that do not semantically align with the action described. Figure 6 provides additional visualizations of our proposed LEGO model. The figure demonstrates that LEGO is capable of synthesizing action frames that are faithful to the user prompts and also preserving the context present in various scenarios. This additional visualization further supports the effectiveness of the LEGO model in generating accurate and contextually relevant action frames. Figure 7 showcases the capability of our model to generate various actions from the same input frame. The initial action, Open Drawer, is already labeled in the dataset. We then introduce 5 additional actions into the user query and synthesize the corresponding action frames using our model. Remarkably, all the generated frames not only accurately depict the specified actions but also maintain the contextual elements from the original input frame. This result underscores the model's understanding of action state transitions and its ability to generalize across different user queries, highlighting the effectiveness of our approach in egocentric action frame generation. Table 1 presents a comprehensive comparison of various image manipulation methods using multiple metrics. The metrics used include EgoVLP, EgoVLP+, Clip, FID, PSNR, and LPIPs. The table clearly indicates that our LEGO model performs exceptionally well, particularly in the EGO-VLP+, FID, PSNR, and LPIPs metrics. The best results in each metric are highlighted, with lower scores being preferred for FID and LPIPs. This table serves as a critical tool for evaluating and understanding the performance of different image manipulation techniques. Table 2 presents the image-to-text metrics of our model and several baselines. The metrics are evaluated on two datasets, EGO4D and Epic Kitchens. The best results in each metric are highlighted in boldface, and the performance of our LEGO model is indicated by the orange row. This table allows for a direct comparison of our model's performance against other approaches, providing insights into its effectiveness in image-to-text tasks. Table 3 provides a detailed analysis of the performance of egocentric action frame generation under various conditioning scenarios. The table specifically examines the impact of enriched action descriptions, VLLM image embedding, and VLLM text embedding individually. The term joined embed is used to denote the incorporation of both VLLM image and text embeddings. This analysis is crucial for understanding how different embeddings contribute to the overall performance of egocentric action frame generation, similar to the findings presented in Figure 4. Table 4 presents the performance metrics of the LEGO model without fine-tuning, without FT, across two datasets, EGO4D and Epic Kitchens. The table showcases the win rates for different conditioning methods, with the best results highlighted in boldface. Notably, the orange rows represent the performance of our full LEGO model. This data underscores the effectiveness of the full LEGO model in achieving superior results, particularly when enriched action descriptions and joint embeddings are utilized. The table serves as a comprehensive evaluation tool, illustrating the impact of various conditioning strategies on model performance. In this paper, the authors introduce a novel problem of egocentric action frame generation. They propose a model named LEGO, which utilizes visual instruction tuning and a diffusion model to address this problem. The key intuition behind LEGO is to use visual instruction tuning to generate responses that depict the execution of egocentric actions. The model is designed to condition the denoising unit on image and text embeddings from a visual instruction-tuned VLLM. Experiments conducted on two large-scale egocentric action datasets validate the advantages of the proposed approach and highlight the contribution of each model component. This work is seen as an important step in understanding action state transition and the controllability of diffusion models, suggesting future research directions in egocentric AI systems, action state transition, image generation, and human skill transfer. Thank you for watching.